everyone. My name is Tuan. I'm from Electrical and Electric Engineering Department at Pelican University and ICNF. Today, I will present our work entitled Unknown Input Observer-Based Estimation of Steering Right Force in Steer-by-Wire System. This work addresses a key challenge in steer-by-wire system that how to accurately estimate steering right force without using expensive or unreadable force sensor while maintaining robustness and stability. This slide illustrates the overall structure of steer-by-wire system. On the driver side, we have the steering wheel module in which includes a steering wheel, a wind, angle sensor, and haptic feedback motor to provide realistic steering feel. On the vehicle side, the front wheel module consists of steering motor, rear heads, pinion angle sensor, right and pinion mechanism, and steering wheel. In such system, right force information is critical for both control performance and driver feedback, but it's difficult to measure directly. This motivates our observer-based estimation approach. We start by the modeling the steer-by-wire dynamic and second as a second model order system in equation 1. The equation show here the capture in inertial damping control input and steering right force. Importantly, the right force and steer and aligning torques and as a number together into disturbance term. For the following established vehicle dynamic literature, the cell aligning torques is approximate using the hyperbolic tangent function as in the equation 2. It allows us rewrite the system into control or oriented space form, where the unknown right force appears explicitly as a disturbance acting on the system. You can see in on this equation. So to estimate both the system state and the right force, we augmented the system model by treating the disturbance as an addition state. This needs to three-dimension augmented state vector consists of the steering angle, angular velocity, and the number distance. You can see on this equation. It needs to, and here is a 2K assumption. In this 2K assumption are made that the first, the disturbance is smooth, and its time derivative is bounded. And the second assumption is brings a condition and so the feasibility of the unknown observer design. These assumptions are standard in the observer-based disturbance estimation and reasonable for a steering system. And I would like to emphasize that here the disturbance number in the state XA. So here how to estimate XA, that we can estimate the disturbance, and then we can estimate the result effects on the steering by wire system. And here, based on the augmented model, we design an unknown input observer. You can see on the equation 7, the observer reconstructs the position state and the disturbance using the auxiliary dynamic system and output injection. A key result here that the disturbance estimate can be extracted directly from the observer set. You can see on the equation 8. When we can to estimate XA based on this equation, and we can estimate the disturbance based on directly the X and and the Z2 here in equations 8. This means the steering rate force can be obtained without adding physical force sensor, which significantly reduce the cost and improve reliability. The observer gain is designed using the rigorous anonymized-based framework. We specifically this circular region in the complex plane to constrain the observer eigenvalues and ensuring both stability and convergence speech. The theorem on the slide guarantees that if the NMI is feasible, then the observer aerodynamic unstable, and the estimation error satisfies the at infinity performance bound. This provides strong theoretical guarantee on robustness against determined variation and modeling uncertainty. So here is our the main result. So in the next step, we validate the proposed method through the numerical simulation. This table summarizes the physical parameter using the steer by wire model, including initial damping, right short motor, compensation, and coefficient. The right force is a reconstruct from the estimation determined using the symbol and separated relationship. Based on this equation, the simulation scenario involves a size sender steering input to emulate realistic driving condition. So in addition to determine estimation, you can see on this figure, the observer also provides accurate state estimation. The slide shows the true and estimated steering angle. Um, you can see the fixed figure shows the estimation of the steering rate force. The soil 9 represents the actual right force, while the dash 9 shows the estimated force obtained from our observer. You can see that the estimated right force closer from the true force, even under dynamic steering condition. The lower plots shows the estimation errors, which converges to zero, confirm the effectiveness of the observer. In the next, is this about the state estimation. The slide shows the true estimated steering angle, and the estimation errors remains small and bounded, demonstrating that the observer does not decrease and the cause steering angle adjustable from while estimates the distance. So we have the conclusion. To conclude, the proposed unknown input observer-based approach for steering right force estimation is steering by system. It's a method we avoid using the force sensor. We provide the theoretical stability and robustness guarantee the via NMI equation, and we achieve the accurate estimation in simulation. About the future work, we focus on the experiment validation and integration with the advanced control strategy for the intelligent vehicle. Here is my reference, and here we would like to thank you for the attention, and we are happy to take answer for the question. Thank you.